Okay, welcome to the first video lesson in the Mathematics for College Technology course. In this lesson we will be reviewing the special triangles, and in particular how to use those special triangles to find the exact sine, cosine, and tangent ratios for the special angles of 30, 45, and 60 degrees. Now to start off, I'm going to show you a very quick and easy way to derive the special triangles in the event that you forget the lengths of the sides required. Now, in order to quickly derive the special triangles, all you really have to remember are a square with a side length of 1 and an equilateral triangle with a side length of 2. And now I'm going to show you what I mean by that. So starting off with a square with a side length of 1, I'm going to split that square in half along the diagonal, creating a right triangle with two 45-degree angles, which of course is one of the special triangles. Now the only side length here that's missing is the length of the hypotenuse. And if I forget the length of that side, I can very quickly figure it out by using the Pythagorean theorem. In this case, the Pythagorean theorem would tell me that the length of the hypotenuse, which is x squared, would be equal to the sum of the lengths of the other two sides squared. So x squared is equal to 1 squared plus 1 squared. Simplifying tells us that x squared is equal to 2, and taking the square root of both sides tells us that x is equal to the square root of 2. And of course I would leave it in exact form because that's the whole point with the special triangles, is we're using them to find the exact trig ratios. So we don't want to convert that to a decimal. So let's summarize that in our first summary box here. So the first special triangle then is the 45, 45, 90 triangle. And please excuse my writing as I adapt to this new app that I'm using to create your video lessons. Hopefully that will improve with time. It's not the most user-friendly app, but for now it's what I've got to work with, so please forgive the messiness of these first few lessons. Alright, so in the 45, 45, 90 triangle, we've got two side lengths of 1, two 45-degree angles, and a hypotenuse with a length of root 2. Now I can use that then along with our SOHCAHTOA to derive the exact trig ratios for an angle of 45 degrees. So sine 45 is equal to opposite over hypotenuse, so 1 over root 2. Similarly, cosine of 45 degrees is adjacent over hypotenuse, so 1 over root 2. And tangent 45 degrees, opposite over adjacent, 1 over 1, which of course just simplifies to 1. Now to derive the second special triangle, we're going to start with an equilateral triangle with a side length of 2. And I'm going to do something similar. I'm going to split this equilateral triangle into two smaller triangles, but this time by dividing it vertically down the center, creating two equal triangles, but we'll look at the one on the right side here. Okay. And in that triangle, of course, we would have a 60-degree angle, because this was an equilateral triangle to begin with. And the angle at the top then would be 30 degrees, half of the original 60-degree angle at the top there. If this was an equilateral triangle with a side length of 2, that tells me that the length of the bottom side, or the base of my right angle triangle, would be 1, so half of 2. And the only side then missing is the height of this triangle, which I will label with an x. Now once again I can apply the Pythagorean theorem to find the length of that side, remembering though in this case that the hypotenuse is actually given. So just be careful when you're applying the Pythagorean theorem to remember that it would actually be x squared plus 1 squared equals 2 squared. If we simplify that, it would be x squared plus 1 equals 4, which tells us x squared equals 3. So x is equal to the square root of 3. And now I have the second of our two special triangles, the 30, 60, 90 triangle. So let's add a summary of that one to our note as well. And then we'll go ahead and find the three primary trig ratios for the 30-degree angle and the 60-degree angle. So here we have the 30, 60, 90 triangle. We can label our third side as root 3, again leaving it in exact form. And now we can come up with our ratios. So starting with the 30-degree angle, sine 30. Now remember, we are looking relative to the 30-degree angle. Okay, so sine 30 would be opposite over hypotenuse, so 1 over 2. Cosine 30, adjacent over hypotenuse, root 3 over 2. Tan 30, opposite over adjacent, 1 over root 3. Now we'll look at the 60-degree angle, and relative to the 60-degree angle, the opposite side would be root 3. The adjacent would be 1. So working through our primary trig ratios then, sine 60 would be opposite over hypotenuse, so root 3 over 2. Cos 60, adjacent over hypotenuse, so 1 over 2. And tan 60, opposite over adjacent, so root 3 over 1, or just root 3 in simplified form. Now the special triangles can be used to solve many mathematical problems, and we're going to look at one of those now. The problem says the angles of elevation from two ships to the top of a nearby cliff are 30 and 45 degrees. The height of the cliff is 100 feet, and we're asked to find the exact distance of each ship from the cliff. So let's begin by labeling those two sides we're looking for in this scenario. So we're looking for the distance of the closer ship to the cliff. Let's call that x. And we're looking for the distance of the ship that's further away from the cliff, and we'll call that y. So let's introduce our variables. We'll say let x and y. I apologize again for the writing. Let x and y represent the distances of the two ships from the cliff. Okay, there we go. So let's start by trying to find the length of side x, so the distance of the closer ship from the cliff. Now, looking then at the smaller of the two triangles in this diagram, we can see that there is a 45-degree angle marked. And this, of course, is a right angle triangle. So we're dealing with the 45, 45, 90 special triangle in this case. Now the 45-degree angle is the one marked, so the length of the opposite side is 100 feet. Right here. That's the opposite side. And we're looking for the length of the adjacent. So of course the ratio that's going to help us here is the tangent ratio. We know that in this scenario, tan 45 is equal to 100 over x. Well, if we're going to apply our special triangles to the solution here, we need to replace tan 45 degrees with its actual value, which is 1. So now we have 1 equals 100 over x, in which case x has to be equal to 100. So there we have half of our solution. Now similarly, looking at the larger of the two triangles in the diagram, we have a 30-degree angle marked, which tells us that this is a 30 60, 90 triangle. Once again, you know the length of the opposite side. We're finding the length of the adjacent side, so we're going to apply the tangent ratio a second time, this time using the 30-degree angle. So tan 30 is equal to 100 over y. Now tan 30 has an exact value of 1 over root 3. So 1 over root 3 is equal to 100 over y. And this would be a case where I could use a bit of a shortcut and cross multiply to solve for y. Okay, so cross multiplying would give me 1 times y, which is y, is equal to 100 times root 3, which I would leave in exact form, and that would be my final answer. So therefore, the ships are 100 meters, I'm sorry, not meters, let's fix that, feet, 100 feet, and 100 root 3 feet from the cliff. Okay. Now, in the next lesson, you're going to be sort of extending this idea of using these special angles to find the exact trig ratios for some angles that are related to the acute angles 30, 45, and 60 degrees. But before we can do that, we need to do some preliminary work here. We need to review some concepts from last year, as well as introduce a couple of new ideas to you. So basically, when dealing with angles, we can only use triangles in trigonometry if we're dealing with angles that are, well, namely smaller than 180 degrees. It would be impossible to represent an angle larger than that by using a triangle. But of course, we often deal with angles that are larger than 180 degrees. A 360 degrees would be a full rotation angle, and in fact, we often deal with angles even larger than that if we're dealing with any kind of circular repetitive motion or any situation where you have any rotation happening at all. So let's remind ourselves, sorry about that, let's remind ourselves of what we do in that particular case. Instead of representing such angles in a triangle, what we do is we represent the angle on the Cartesian plane instead. And I think most of you would have seen this before, or should have certainly seen this before. When looking at an angle on the Cartesian plane, we always place the initial arm of that angle along the positive x-axis. So let's label this as the initial arm. The angle then in standard form rotates counterclockwise, as indicated by the arrow in your diagram. And the arm that's actually rotating we call the terminal arm of the angle. So the vertex of this angle always stays at the origin. Okay, and the second diagram you've got there just goes to show you that it is possible then to represent an angle of any size. And when dealing with a rotation, we could rotate this as many times as we wanted to. So picture a wheel spinning, a Ferris wheel going around, that type of thing, okay, where you're dealing with circular motion. So if I want to represent, say, a rotation of 420 degrees, I would start at the positive x-axis, rotate one complete rotation, that would be 360 degrees, add on another 60 degrees, as is indicated in your diagram, giving you a complete rotation of 420 degrees. Now at this point, I'm going to have you stop what you're doing and refer to the second part of the video, lesson 1.